In this video, we're going to look at a few examples of using Newton's method. So first of all, let's remember what Newton's method is. It's a root finding method or algorithm. If you're given a particular function and you know that there's a root somewhere, so you know there's a 0, then it says that if you have an initial guess, then you can use a formula that has iterations, gives you a sequence of iterations, and each additional iteration in the sequence will be a better and better approximation. Now, there are some technical things to keep in mind with this. It doesn't always work. There are some cases where you can have some bad behavior. But generally, if you have a good initial guess, you're more than likely going to have Newton's method converge to one of the solutions of the function. So let's start with this first example here. So it says, use Newton's method to approximate the value of the fifth root of 37, correct to 6 places past the decimal. Okay, so first of all, there's no function given here, so we have to kind of translate this into what the function is going to be. So we're really trying to find an approximation for x equal to the fifth root of 37. Now, this you can look at as declaring a value of x, but you can also look at it just as an equation. And as an equation, it's actually equivalent to x to the fifth is equal to 37. Right, that's what the fifth root of 37 is. It's the number when you raise it to the fifth power, gives you 37. And that's a unique value because it's an odd power. And this is then equivalent to x to the fifth minus 37 is equal to 0. So what we're going to see in these 3 problems we're going to look at is if you're trying to find a solution of an equation, then what you can do is subtract one side of the equation to the other, and you get 0 on the other side. And so you've reduced the problem of solving an equation to finding a 0 of a particular function. So here we could call this, for instance, f of x. So we'll let f of x equal x to the fifth minus 37. And what we're trying to do now is figure out what is the 0 of this. So let's remember what Newton's method, what the Newton formula is. It's the iteration formula. So the iteration formula says that each additional sequence, each additional term in the sequence of iterates is given by the previous term. So the n plus first number or guess is given by the previous guess, and then we subtract off a fraction, and it's the numerator is the value of the function at that guess divided by the derivative evaluated there. Now, where this comes from is this comes from thinking about the tangent line approximation to a function at a point. And so this is really giving you the 0 that you would get from the tangent line or the linear approximation at a point. But that 0 ends up being generally, most of the time, a better approximation than the previous. And so then what you can do is you can feed back that 0 into this same iteration formula, and you just get better and better linear approximations near the solution, and your sequence of guesses gets closer and closer to the actual 0. So we need to choose, whenever we're using this, we need to choose an initial guess. Now, since we know that 2 to the fifth is 32, 3 to the fifth is, so this is going to be 243. Clearly, the fifth root of 37 is going to be between 2 and 3, and it's going to be probably much closer to 2. So 2 is probably a good initial guess here. So let's start with that. x1 is equal to 2. And so we're going to feed this initial guess, x1, into our formula. Now, I'm going to do maybe the first one by hand, but what we're going to see really soon is that we're going to have to use a calculator. And actually, I'm going to show you how you can do this very nicely on WolframAlpha so that you can just change the number and you just hit enter each time, and you'll very quickly get the sequence of iterations. So here, x2, so the next term here says take the previous term. So it's going to be x1 minus f of x1 over f prime of x1. We do need to figure out the derivative. Okay, so let's do that. Actually, let me erase this 2 to the 5th and 3 to the 5th here, and we can put in the derivative. So this is xn minus, so f of xn is just going to be xn to the 5th minus 37, and then over 5xn to the 4th. So that's really, that one on the right, that's really what we want to look at. All right. So here, x1, so this is actually going to be x1 minus x1 to the 5th minus 37 over 5 x1 to the 4th. But x1, we're starting off as 2. So it's 2 minus 2 to the 5th minus 37 over 5 times 2 to the 4th, which is 2 minus 32 minus 37 over 5 times 16. Now, the 32 minus 37, of course, is negative 5. So what we end up with is 2 plus 5 over 5 times 16. Okay, the 5's cancel. So we get 2 and 1/16. So 2 and 1/16 is 2.0625. Okay, so that's our second term of the sequence. Now you can see here that if I was going to plug it back in and try and do it by hand, I'd be taking 2.0625 to the 5th minus 37. So we're not going to do that calculation by hand. We're going to use WolframAlpha to generate the next terms of this sequence. Okay, so let me show you how to do that. I'm going to go to WolframAlpha and show you how to do this. Okay, so here we are. Make the font nice and big so you can see it. Okay, so the wording that you can use here, this isn't the only wording you can use to do it, but this one's, I think, very natural. So what I'm going to type is evaluate. Okay, so if you want to evaluate an expression at a certain value, you can just do evaluate this at something. So the expression that we want to evaluate is the right-hand side of that formula. So it's x minus, and then on the numerator, we had the x to the 5th minus 37, okay, over, and then 5x to the 4th was the derivative in the denominator. Now, we don't have to put the x sub n because we're just saying evaluate it at x. So we're going to evaluate this at x is equal to 2.0625. Now, something here that is helpful to know, at least with WolframAlpha, is it tends to want a lot of extra zeros, or extra digits, if you want to get a good decimal approximation. I'm not sure why this is. It has kind of default set in. It only gives like 4 places past the decimal unless you specify something else. So what I'm going to do is just give 10 places past the decimal. So I need 6 more zeros here. So there's 6 more zeros. And then I'm just going to hit the equals compute input over here. And what you want to do after you enter this in is, first of all, make sure that you got the expression right. It's easy to get parentheses mixed up or type something in wrong. So double check your expression. It will typeset it, and you can check. And then see what the next term is. Okay, so we do this. Okay, so I'm going to check here. Input interpretation. X minus, and then there's a fraction, x to the 5th minus 37 over 5x to the 4th. So that's the correct expression. That's the correct Newton's formula, where x is equal to 2.0625. Okay, great. So now I've got my second term here, 2.058936514. Okay. So so let's take that number, and now what you want to do, this is really neat. You can just go back up here and just enter that, right? That output becomes the input. So I'm just going to do 0.58936. Now that would be 6 places past, but as I said, I'm going to go to 10, just to go a few past what I need so that I can see that I've got all those digits agreeing, and also it forces it to give me more digits. So 0.589365143. Okay, so we're going to enter that. Now this would be x4, right? So x1 was the 2, x2 was the 2.0625. We just got x3. Now this would be x4. This 2.0589241366. And you notice that we're already agreeing, it looks like, to 4 places past. The previous one was 0.5. You can check here. It says 2.058936. This is 0.58924. So we're already correct to the nearest 10 thousandths. So let's do this again. 2.0589241366. Okay, 0.589241364. Okay, but we have our 6 digits here. So once I've got 0.58924, 0.58924, you can see they're going to agree in those 6 digits, no matter how many other terms I'm going to get. So we have convergence to that degree of accuracy. So that is our answer. It's 2.058924. So I'm actually going to write these down just for the notes. You know, we did it in real time there, but so 0.5, x3, the third number was 0.58936. x4 was 0.58924, and then it was 1366 after that. And then we got to x5, 2.0589241364. Okay, so now the point is we agree in the 6 digits. So our final answer would be the 5th root of 37 is approximately equal to 2.058924. Now, if you were studying this more rigorously, or you're really getting into what's going on here, there's a class for that. It's called numerical analysis. It's usually what you would take as an upper division class if you're a math or science or computer science major. And in that case, what you would do is you would study the rate of convergence. And it turns out that Newton's method actually has a pretty good rate of convergence. So we would say that the rate of convergence is quadratic in general. There are exceptions, but we would say that it's a quadratic, which is a pretty good rate. It can be improved upon, but this is a very simple kind of straightforward idea. And the fact that we get that kind of convergence is good. So so you're starting to see the power of calculus here. Okay, let's go to the second problem, and in this one, we're just going to be given an equation to solve. So finding just a solution of an equation, and so what we're going to have to do is translate that into the root of a function, and then find the derivative and get our formula. We'll do much the same thing, but I'm going to graph the function so that you can see what's going on geometrically as well. Okay, so we are going to solve this equation 2 sine x is equal to x squared. And this says it has a unique positive solution. Obviously, 0 is a solution. If you don't see that immediately, you can check it easily. Sine of 0 is 0, 0 squared is 0. But it has a unique positive solution. And so we're going to use Newton's method to approximate the value of this solution correct to 6 places past the decimal. So what I'm going to do is show you the graph of this. And, well, okay, first of all, let's translate this into a function. So 2 sine x equals x squared. If I subtract x squared from both sides, finding a solution of this original equation is equivalent to finding a solution to 2 sine x minus x squared is equal to 0. Okay, so this is going to be our f of x. Let's find our f prime over here. So f prime of x is going to be 2 cosine minus 2x, which we could factor out the 2. So it's 2 times cosine x minus x. So what is our formula here? It's going to be xn plus 1. So the next term is going to be the previous minus 2 sine of xn minus xn squared, all divided by 2 cosine xn minus xn. Okay, that is the iteration formula. All right, now let's take a look at what's going on here. You may kind of have a feeling for what's going on already. So the function starts at 0. So look at this 2 sine x minus x squared. So the function obviously starts at 0. The sine function, if you think about what the sine function and x squared looks like, sine function increases more rapidly than x squared between 0 and 1. So this is going to increase. And what it ends up doing is it increases to a certain maximum, and then it starts decreasing, it falls back down, and it pretty much decreases from that point on. You can see the derivative is 2 times cosine x minus x. Once the x term overtakes the cosine, it's just decreasing all the way to minus infinity. So here's what the graph of this function looks like. Okay, so you can see there it's 0, goes through the origin. It actually is decreasing, or sorry, it's increasing all the way up to there. So it shoots off to minus infinity in either direction. It does increase to this maximum value up here. So there's the solution, the positive, unique positive solution that they're talking about. You can see there's only one of them there. So now this one here, you can kind of see, even if I didn't click on it, you can see it's between 1 and 2. So why don't we start with an initial guess of, say, 1? Now, that's pretty far off, but still, it's a nice round number. And so let's start with 1, and let's see how many terms it takes to get us before we start to zone in on this solution. So this right here says it's about 1.404. Now, we need more digits than that, but we should be getting a number that's about 1.404. All right, so we'll start off with x1 is equal to 1. And I'm not going to rewrite the second term here. What I'm going to do is just go back to WolframAlpha, and we'll use the same kind of thing that we did before. We're going to evaluate the expression. We just keep changing the numbers each time. Okay, great. So we're back here. So we need to change this function. I still have the old one here. So now instead of that, it's going to be x minus. So on top we have the 2 sine x minus x squared, all divided by 2 cosine x minus x. So double check your parentheses there. Make sure you got the right amount. Yeah, that looks okay. And we're going to start at 1. And I'm just going to add the 10 zeros to 5, 1, 2, 3, 4, 5. Just to make sure that it gives me some nice digits. Okay, here we go. Double check your expression. Let's see, xn minus twice sine xn minus xn squared all over 2 times cosine xn minus x. That is the right formula, starting at 1. Okay, and we get 1.742816 approximately. Okay, so I'm going to put in 74281639. 68. Okay, so I'm just going to do the 10 digits each time until we recognize that we have 6 digits agreeing. So here's our next one, 1.464. So you can see we're already getting much closer to that root. So here we're at 464,098,2834. Okay, let's see what the next one is. Okay, 1.407. So notice we've gone through 3 iterations here. This is x4, and actually we only have 1 digit locked in, 1.4. So, you know, if your guess is a little further off, it's going to take a few more terms. It's not going to be like within 2 or 3. It depends on what your initial guess is. Okay, let's do one more. Now we should really start to see some more agreement here. 4044202. Okay. Now you can see we're really starting to get closer to that number. Okay. One of the nice things about Newton's method is even if you mistype some of these digits, it doesn't matter. You just keep doing it. That error will just be absorbed into Newton's method. So unless you have to get the exact sequence for the homework. 40441482. Okay, so how much agreement do we have here? We have up through 4044. After that, there's a little bit of disagreement, so we continue. 4044148224. 4044148241. Okay. Okay, now what do we have? 1.4044 14824. Okay, so we've got that much. So that's 6 digits. So it's 1.404414. So that's to 6 places past the decimal. So again, I'm just going to write these down just for the notes that this is what you should have gotten. 742816. 1.46498. 0.407028. 0.40420 x6. 1.404414 8241, and then the last one, which confirms these digits, is 824. Actually, I think it agreed. I'm not sure about the last digit, but okay. So the unique positive solution is approximately 1.404414. Now, just to be clear, this is probably the best that we can do as a numerical approximation. When you have these equations here with these transcendental functions, so that just means like trig functions or inverse trig or exponential log or things that are worse than that. When you have those kinds of expressions inside of an equation and you're saying, you know, what's the solution? You're not going to be able to write down the answer, you know, in symbolic form. It's just not going to be able to be done almost all the time. So this is really the best we can do. We can just say, you know, I can't write down what the answer is. I mean, maybe I could define some kind of new function that has something to do with equations like this, and then, you know, define it in terms of that. But that's kind of cheating a little bit. It's not really allowed. So in terms of the normal functions that we have, we just can't write down the solution. The best we can do is get an approximation. All right, we're going to do one more problem. This is going to be a question that's stated not in terms of finding a solution of an equation, but it's going to say approximate an inflection point. So we're going to have to do a little bit of work up front to figure out exactly what equation we should be trying to solve. So we're given this function, e to the x over 1 plus x squared, and we're told, so we can assume this is true, it has two distinct inflection points. Okay. One of these is at the point 1 e over 2. So obviously, if you take f of 1, it's e to the first over 1 plus 1. So it's e over 2. But there's another inflection point. Find the x coordinate of the other inflection point, correct to 6 places past the decimal. So let me show you the graph of this. You could sketch, so you could use the curve sketching steps that we went over, calculate the first and second. Well, we're going to calculate the first and second derivative here, but you could do the curve sketching stuff and get a pretty good picture of what this looks like, but that's not the point of this particular video, so I'm just going to go and show you what the graph looks like at Desmos. Okay, so this function is increasing everywhere, if you notice that. Now, if you think about what happens as we go out to plus and minus infinity, as you go out to infinity, you've got the e to the x on top, and then a 1 plus x squared on the bottom. The exponential is going to win out there. So that's why it's shooting up to infinity. As you go to minus infinity, the denominator is getting bigger, so it's sending it to 0. But also, it's e to the minus infinity. So it's, it's like it's both of the numerator and the denominator are pushing it towards 0. So you can see as you go out to minus infinity, it's very quickly going to 0. It's increasing, but it has, it speeds up and slows down. So it appears to be concave up quite a ways, up to -1. And then it looks like somewhere between -1 and 0, somewhere along there, it seems to change for a little bit to concave down. Okay, so right around here, just right around 0. And then it seems to go, and then remember, 1 is an inflection point. So that's right there. So that's an inflection point. That's where it's changing from concave down to concave up. So it starts off concave up, then down, then up. So there's the one inflection point. I would say the other inflection point is probably somewhere around here. Somewhere right around here, right? You can see. So the question is, exactly where is that? So now let's choose an initial guess. I think it's probably quite a bit more than that. Maybe we could choose. Why don't we start with like why don't we start with minus 0.25? That looks like a good one to start with. Okay. Because it's got to be pretty close to that. We can see by the graph. Okay, so let's do that. So we have to calculate the derivatives. All right, this is kind of a mess for the derivatives, but let's go through it. Okay, so it's denominator, derivative of the numerator, minus numerator, derivative of the denominator, all over denominator squared. And when we clean this up, so if we take out e to the x, we've got x squared minus 2x plus 1. So that's going to be x minus 1 all squared, e to the x, over, I'm going to switch this to x squared plus 1 all squared. Okay, so that's the first derivative. So far, so good. Now, the second derivative is a little bit more involved. All right. So let's see, what's the best way to do this? So actually, I think one way that this might be better is to just look at this as a product rule where the rational part is one factor and e to the x is the other. In other words, look at this as x minus 1 squared over x squared plus 1 squared all times e to the x. I think that's probably going to be the best way to consider this. In fact, since these are both squared on top and bottom, why don't we just take that square out? Yeah, I like that. Okay, so let's do the product rule. It's going to be first derivative of the second plus second derivative of the first. The reason I like doing this is because the e to the x, we know that its derivative is going to be e to the x, so it's going to be the same whether it's getting differentiated or not. So first, so we got first derivative of the second, which is e to the x, plus second derivative of the first. So there's the second, and then the derivative of the first. Okay, so what's the derivative of this? Well, it's 2 times all of this stuff to the first, right? So the general power rule would say 2 times all this stuff to the what? To the first, but then times the derivative of what's inside. This is the tricky part. So what's the derivative of what's inside? Now we have to use the quotient rule. It's denominator derivative of the numerator minus numerator derivative of the denominator all over denominator squared. Okay, so what can we do here? So let's factor out everything that we can possibly factor out. And actually, on the numerator here that we just did, let's see if we can see what that comes out to be. This is going to be a minus 2x squared. It's a minus 2x squared plus 2x. Correct? Yeah. So that's all that. So we've got x squared plus 1 minus 2x squared plus 2x. So altogether, that's going to make a minus x squared plus 1 plus 2x. So a minus x squared plus 2x plus 1. Now, what's the most that we have in common? Well, we certainly have e to the x. We have an x minus 1 over x squared plus 1 all to the first. And I think that's about it. Oh, actually, no. We have another factor of x squared plus 1 here. So all of this times e to the x times, now what's left over? Let's see. From the first term, we're just missing an x minus 1 on top. So x minus 1. From the second one, we're missing quite a bit more. Let's see. So we're missing, we got x minus 1, we got that. So we're missing a plus 2 times minus x squared plus 1 plus 2x. And then this is all over the other factor of x squared plus 1. All right. So what we need to do here is get a common denominator. So we got over x squared plus 1. This is going to be times x squared plus 1. Okay, so I'm going to put the e to the x out in front. So it's e to the x times this times, let's see, that x minus 1, x squared plus 1. That's going to make a x cubed. All right, x cubed minus x squared plus x minus 1. Okay. X cubed minus x squared plus x minus 1. And then we've got, if I distribute the 2, minus 2x squared plus 2 plus 4x. Okay, so let's put all that together. It's x cubed. And then we got minus 3x squared. We've got 5x plus 1 all over x squared plus 1. All right, so now obviously, we could put these together to make cube, but actually this is as far as we need to go because we need to know when is this going to be equal to 0. Okay. So e to the x can never be 0. The x squared plus 1 factor can never be 0. So you can see there the x minus 1, so that explains what's happening at 1. Now, what's happening over here is that means our other inflection point has got to be coming from that cubic. So it's got to be a root of the cubic. Okay, so our inflection point, our other inflection point, must occur at a root of this cubic polynomial. So why don't we call this g of x? So then it really amounts to, well, let's find a root of this g of x with our starting value of minus 0.25. So the point I'm getting at is we don't have to use the entire f double prime. A lot of people would think, oh, if I need to find a 0, I need to find where f double prime is equal to 0. They're going to use the whole f double prime. And so they're going to be looking at f triple prime, which is not what you need to do. Once you determine that the inflection point the other inflection point can only occur where this cubic polynomial is 0, then just focus in on the cubic polynomial. Throw away the other factors. Okay, so just looking at this g of x. So this is going to imply g prime of x is equal to 3x squared minus 6x plus 5. Okay, so now we can get our iteration formula. We're going to use x1 is going to be, let's see, we said to start at minus 0.25, and xn plus 1 is going to be xn minus the cubic on top, and then all divided by, I can't draw a straight line that long, all divided by the derivative on the bottom. So 3 xn squared minus 6 xn plus 5. Okay, so that should do it. Let's go to WolframAlpha now. I'm not going to type in all of this. This was quite a bit of work just to calculate the derivatives. So, so using WolframAlpha, let's just keep track of how far we have to go here. So again, we're starting with minus 0.25. So minus 0.25, and then we got to change our function. So on top was the it was x cubed minus 3x squared plus 5x plus 1. And on the bottom, 3x squared minus 6x plus 5. Okay, so let's do this. Double check, it looks right. Okay, so minus 0.182243. Okay, so let's keep track of which one this is. So our answer right now is x2. We're on the second term. 182243. 1, 2, 3, 4. Add a few zeros. Now we're going to get the third term, x3. Okay. 17951300000. Now we're going to get x4. Okay, I don't know why it's being stingy with the digits. Let's see, 179509. I just keep adding more zeros. Okay, this is going to be the fifth term. Okay, there. I just don't understand exactly. Just add more zeros if it's not working. 179509 0. Okay. So I think we're already agreeing to this. So the fourth and the fifth terms are already agreeing. It looks like it's minus 0.179509. So I'll say using Wolfram Alpha ... We get x5 is about minus 0.179509. And those 6 digits are going to be locked in. So that is the x-coordinate of the other inflection point. So, all right. What I'm going to do just to close up here is I'm going to go back to the graph, and I'm going to show you the graph of the second derivative so you can compare the graph of the concavity and see how it matches up with what we were saying about the original graph of f. So the black graph, that was our original function. So there's the one inflection point, and then we said the other point. So that's an intersection point. That's not the inflection point. The other inflection point turned out to be, so notice it right there, about minus 0.18. Now, remember that that inflection point is going to happen when this green second derivative is 0. Notice how the second derivative here, it's positive, so it's saying it's really concave up for a while. And then it goes back concave down. It slows down, comes to a plateau. So down there, it's really concave down for a while. And then it comes back up. There you can see the other inflection point, which is right there. Right. Come on. Right there. And then it's gradually increasing in concavity from that point on. So definitely this graph of the second derivative matches up with what we're seeing in the first graph. And if I zero in here, so if I come closer here, I'll start to get more digits. Just a little bit of zooming in here, I've already got minus 0.1795, which does agree to the 4 decimal places for us. So that that should be telling us that. So there's the function over there. So that's telling us that it's confirming that the number that we got really is the right inflection point. Okay, so that is Newton's method. Very powerful method using some really kind of straightforward applications of calculus to do some really amazing things. This is a method that was discovered pretty soon after derivatives were developed. It was one of the very first really powerful applications that was used to solve some really direct applied problems. So, all right. So this finishes off this this whole chapter. Next, we move on to integration. That's the second branch of calculus, and then we're going to talk about the fundamental theorem of calculus and bring everything together in a nice little bow at the end, see how the 2 branches of calculus are related to each other, the differential and integral calculus.